Thank Professor and Vice Dean Rudinskas. Thank all the faculty. Thank the students, okay, for participating, joining us. I'd like to thank Clarissa, Rafaela, Fabio, and um, sorry, Antonio and Franco for the assistance they did. And I want to start by introducing myself. Um, I I am Brazilian, but I'm currently in Montreal, Canada, which, believe it or not, is colder than it is in Vilnius right now. So this is what I say. Montreal is always colder than anywhere else. Okay, and right now it's 0 degrees Celsius out here. We even had snow last week, so it's unbelievable. So Fabio would have some issues developing the ECS system, okay, for Montreal. Maybe we need an ECS system here to make things more habitable, okay. As you said, okay, so I am Brazilian. I live in Montreal, okay. I have a degree at University of Brasilia in BSc, and I have a master's in University of Federal University Itajubá, where I worked a little bit on gas and vapor turbine cycles, Brighton and Rankine cycles, okay, when we use biomass gasification, okay, so basically on the pulp and paper industry that I was working with. I have been working a little longer than 20 years on the aerospace industry. I've had the pleasure of working on all my colleagues and friends here, okay, not only at Embraer, where I was for 10 years. Then I left a little bit. I worked at Bombardier Aerospace, and and then I joined the. As you can see, my name is, maybe you're a little wondering where comes the von Tiesenhausen, so I have to apologize for that. I understand that you have some issues with what they call the ethnic Germans, the Baltic Germans, but I have no response. My grandfather used to live in Estonia, okay, so he left Estonia when he was 15 years old, and he went to Brazil. So I know that just like we have with Argentines, you have with Germans, but I've always been very interested in learning about Estonian, Lithuanian, Latvian culture and history. It for me is fascinating. Okay, I was very close to visiting your country in Estonia last year, but COVID stopped me from doing that. Okay, but I will. I hope to do it very soon. Okay. So as I said, I'm a mechanical engineer at University of Brasilia. I have combined gas vapor in the University of Itajubá, a post-graduation aeronautics engineering. As I said, I worked with all of them at Embraer from 2001 to 2010, and I was the air systems and oxygen system product development. At Embraer, I worked a lot with Rafaela we were like dealing with interior systems and AMS. With Fabio was a very good friend of mine that we worked together with, especially when we did the Embraer 190 certification for the ETOPS 120. Okay, we worked a lot on the avionics schooling, the CPCS, all the studies. Also worked with Franco on bleed and all the 170 and 190. And especially with Clarissa when we're working with safety. And Clarissa worked with the system, which is the fuel system, and I work with the oxygen system. So you're always forgotten, okay? People always remember us when it no longer exists. They take for granted the fuel system and the oxygen system, okay? So when it happens, when there is an issue, okay, they remember that it exists, okay? So the fuel system and the oxygen system are extremely important, okay, as every other system on the aircraft when designing it. And we'll be talking about the crew and the passenger oxygen systems on the aircraft. Bombardier Space, I worked with programs like the Global 7000, the Q400 cargo combi, when they expanded the cargo compartment, and I was working with a lot of ECS, fire suppression, oxygen system, and CPCS on that. And the C-Series, when I was devoted on the flight testing aspect, okay, especially on pressurization, oxygen system, and smoke penetration and smoke detection and avionics schooling. And then I met all my friends again at Mitsubishi Aircraft. And at Mitsubishi Aircraft, I was assigned the responsibility of designing with a very good friend of mine who's not, of course, is not here, but Shimomura's son, and we were supposed to design, develop, flight test, and certify the oxygen system of what was the program called MRJ M90 that unfortunately, for various reasons, could not be completed. Okay, I'm also a member of the Aircraft Oxygen Equipment Committee, which, by the way, it started this week, their spring meeting, and I added the link, which is very important. All the oxygen standards, all the airspace standards, airspace recommended practices, and information practices, they're all located in this link where I have. Okay. So before I start, I'd like to say something like you. So whenever we work with aircraft or we work with anything, okay, we have to focus on things like that. We have to always have an open mind, okay? Because when you go to the aircraft industry, you'll be dealing with a lot of different technologies and a lot of different mindsets, okay? Each one is going to try to save on their own. If you don't think the aircraft as a whole, as a product, we're not going to complete that. So I put these two scenes here. One we see, like we have Picasso and Salvador Dali. So how they see an egg, okay? They see it differently. Also, we have Sophia Loren and Jane Mansfield. Jane Mansfield was very famous for Westerns, okay? She died very early. And Sophia Loren. So some people say, where is Sophia Loren looking at? Some people say they're looking at her jewelry. Others would say she's looking at something else, okay? That doesn't mean that one idea is different from, is wrong or is the most certain. What we have to know is when designing an aircraft, we have to comply with requirements. We have to have open mind. Many times we're gonna have to relent and give in and say, okay, I want an oxygen system. Like Fabio was talking about microprocessors for the ECS system in order to have some kind of monitoring. That might not be possible because of EMI regulations. So we always have to find a way in between. So, and this I'm going to, so I shared some quotes from very interesting people, but I'd like to say for successful technology, reality must take precedence over public relations, for nature cannot be food. Richard Feynman was a physicist, amazing, and he worked at NASA, and he said that when we had the accident with the Challenger, okay? So this is something you're gonna go when you go to the corporations. A lot of schedule driven, a lot of money is involved, but we always have to have transparency and comply with the regulations. And I put a Lithuanian proverb here that I found. I'm not going to say it easily, I'm not going to dare to pronounce it, but it's like, it's easy to say, but it's hard to do. Okay, I think this is what it says, okay? In Portuguese, we have a very similar one, okay? So it's very easy to say, let's build an aircraft, let's go and face an aircraft, but designing an aircraft is one of the most difficult challenges everyone has, okay? It may be very successful at the end. When you see an aircraft flying, the one that I have witnessed when flying with the 170, 190, that was very good, okay? And all the aircraft, the C-Series, the 400, and all the ones that we worked with, it's very rewarding. But I'm going to tell you it's very challenging as well, okay? And we have always to balance and keep an open mind. And see that sometimes we have to keep calm, okay? Like we have a bird strike here, and oh great, now and there goes my head. So we always have to keep calm, and I have to tell that to myself many times, okay, when we are dealing with a difficult situation. And believe it or not, when you're designing an aircraft, there will always be difficult issues coming up, okay? Like this guy saying, oh my God, I always sit with strange guys next to me, and here comes the strangest guy, okay? So what we have to have an idea about. So the agenda for the oxygen system is, we're gonna have types of aircraft oxygen systems. I'm gonna have a basic design, installation, and safety requirements, and I'm gonna have the oxygen system requirement evolution. I wanna tell you that you're free to interrupt me anytime, okay? I don't mind at all. So if you have a question at the moment, or take a note, and we'll be answering all the questions at the end of the presentation. I wanna share the whole experience that I did And I've always worked with air management system as a whole, and especially oxygen system on the design, development, safety assessment analysis. The safety assessment, which is a very, every engineer must know how to deal with safety, even if you're not working with, and excuse me. And I'd like to say that, and also on the ground and flight testing of the aircraft, some requirements, Rafaela is always going to say, so the FAR 20, the FAA, EASA, or ANAC, or Transport Canada requirements, when we design an aircraft, we have to demonstrate compliance. How are we going to demonstrate compliance to that specific requirement? Is it going to be through design? We're going to do an analysis. We're going to do a flight test. So we have the means of compliance. Okay, so the means of compliance, approximately 9. It can be an inspection, can be a design, can be an analysis, but many times, most of the times, we're going to have a ground and a flight test. So preparation, discussion, technical discussion are essential for if you want to come up with a successful outcome. Okay. So the types of aircraft system for aircraft, we have the gaseous type design, the chemical type design. We have a liquid type design that I'm going to ask you the permission to not talk about. It's a very long issue, and so it would be dedicated a different one, and very little is this technology applied on civil aircraft. Okay, I myself have never seen it. And we have a new one, which is the onboard oxygen generator system, which is very common on military for military aircraft, and right now is being studied for civil aircraft. Okay, and I myself participated in a development of a study to use O-box system. The main reason is the O-box does not provide the amount of oxygen for high altitudes. Okay, so we do not comply like with 100% oxygen above 35,000 feet, which is necessary whenever we have a depressurization event. However, at lower altitudes, the O-box can be applied. Okay, so right now some corporate jets, okay, small jets are starting to study the use of O-box, and the reason is we eliminate a lot of weight and failure modes, okay, that the other systems have. Of course, because it's a new technology, people are always reluctant and even reactionary to accept it. Okay, but I think it's one of the things, like Fabio said, about the future of ECS, especially on the more electric aircraft that Fabio brilliantly showed. We'd like to say that O-box may be a future, maybe a technology of the future, okay, pretty soon. So what I want to show is, sorry, I'm just trying to, okay. What I'm going to show is, first of all, we have the gaseous type system. What is basically the gaseous type system? We have systems like storage, distribution, supply, and indication. Gaseous systems are basically that, of course, whenever we provide the oxygen, and I'd like to say one thing very important, ECS, the environmental control system already provides through the backing flows and the inflow on the cabin, which we calculate according to, there's a FAR requirement, FAR 25-131 alpha, which establishes what is the acceptable pounds per minute, so mass flow, okay, that we have for each cabin occupant. It's something like 0.55 pounds per minute for each cabin aircraft whenever everything is working appropriately. If we have like a failure, like a single pack, it drops down to 0.4 pounds per minute. However, so the oxygen is being distributed and at levels that are fully acceptable. Of course, that we're flying at high altitudes. I can give an example of the 170, 190 and the C series, and like the Airbus, and they fly above flight level 400, which is like 41,000 feet, 43,000 feet. We can feel a little sickness, or like feel a little tired, because of course the oxygen system, it's the oxygen content because of the pressure, the partial pressure of the oxygen at high altitudes may not be sufficient. However, it is absolutely, it meets the survivability and the issues. Okay, this is very extremely well maintained in the ECS system. However, when we lose the pressurization system, or when there is a pressurization loss from the cabin pressure control system or from the environmental control system, we have a failure from the bleed system, from the packs, or the outflow valve fails, anything like that, like Fabio demonstrated on ECS, we're going to have to provide not the oxygen, but the supplemental oxygen. Okay, so this oxygen is always providing a gas form, of course. Okay, so regardless if it's a gaseous type or chemical type or liquid. However, what we do is we talk about storage. The gaseous type is based on, I'm just going to go quickly to that one, is based on cylinders. Okay, so we have DOT, United States Department of Transport, exempt or issued cylinders, which, sorry, I have to go up. So these cylinders are located, and they're usually used for both ways. Crew oxygen systems are based on gaseous systems. Okay, the reason is the amount of oxygen, the supply, the duration of supply of oxygen to the crew, each crew member must be 2 hours of oxygen, okay, for each flight crew member. So this is what one of the operational, the FAR 121 says. You need to provide a minimum of 2 hours for each flight crew member. So that 2 hours, they are separated in the emergency time and also on some kind of reserve time. So we calculate that the aircraft is going to take like 10 minutes to descend to 10,000 feet or safe altitude. So have this in mind. 10,000 feet is the altitude at which supplemental oxygen is no longer required. Okay, so at that altitude, we can, through our metabolism, the oxygen in the cabin, okay, that comes because of a ram air, like Fabio said, whenever there is a failure on the, so the CP is the ECS provides bleed system through the packs. If one bleeds fails, we still have the packs functioning. If the packs fail, we can go to APU, or the unit that will provide a pneumatic source and pneumatic energy at lower altitude, something like 15,000 feet. If the APU fails, we go down to 10,000 feet, and we have the emergency ram air ventilation. At 10,000 feet, our body, our organism, our metabolism is able to produce, to survive without the need of supplemental oxygen. And the reason is not because there is no oxygen at high altitudes, it's because the oxygen partial pressure at 10,000 feet suffices to provide, so the pressure that exists, the atmospheric pressure, 10,000 feet, is enough to have us inhale and exhale the necessary amount of oxygen for survivability, okay? So we have the storage, which is, so when we talk about gaseous, we talk about the oxygen being stored in the gaseous form. So we have the cylinder, okay, which is stored usually 1850. I'm going to show you later, but 1850 psi, which is the nominal pressure that the oxygen is stored, okay. And then we have the distribution system. Distribution system consists of the hoses and the lines, okay, that will take the oxygen to the flight crew, or whenever we have also a gaseous type for cabin occupants. I want you to understand that I call cabin occupants, anyone that goes in the cabin can be the pilot. The pilot goes to the toilet, he becomes a cabin occupant, okay? So the flow requirement for the cabin occupant is different from the flow requirement for the flight crew. The reason is, for the cabin occupants, we have to have survivability. For the flight crew, we have to provide an enormous amount of oxygen, higher than the ones for the cabin occupants, so that they can perform all the procedures whenever you have an emergency event. Oxygen is used in two events. Whenever we have smoke event, like smoke in the cockpit, or smoke that penetrates occupied compartments, or when we have a loss of pressurization system because of hypoxia. The flight crew is oxygen protects from fire protection and from the smoke fumes and for hypoxia. The cabin is only for hypoxia. There is no way that we can protect the cabin occupants from smoke fumes. Okay, so the hoses. So we have several hoses. We may have a hose like this one to refuel the cylinder. We have a hose to measure, okay, that can measure the amount of oxygen, okay, that is available, which is also a requirement. There is a requirement that says we have to provide the amount of oxygen available to the flight crew in flight. And we also have the hoses that will discharge the oxygen overboard, which is also a requirement, 1453 FOX, whenever you have overpressure event in the cylinder. So after the cylinder, we have a regulator here, and the regulator will drop the 1850 PSI to approximately 60 to 90 to 85 PSI of pressure that will be sufficient to deliver, okay, the oxygen to the flight crew. And if it's a gaseous cylinder also for the cabin occupants, we are going to have distributed into the last. So we calculate, of course, the math lab and everything, the pressure loss along the lines to make sure that the most critical distance will have the required flow requirement. The supply, as I said, will be the masks. Okay, so the masks will regulate. We have also a second regulation of the oxygen provided in case of the flight crew masks, not in the case of the masks, unless you have some kind of systems, let's say computerized system that will provide the necessary amount of flow according to the altitude. And we also have the indication system, which consists, I'm going to show everything in the following slides, which would be basically analog indication equipment, like a pressure gauge that is usually located whenever for the maintenance people to analyze to see what would be the pressure while you're refueling the cylinder. At this place, we have isobaric curves, because you can, like here in Canada, and I believe that in Lithuania as well, the temperature can drop down to minus 25, minus 30 degrees Celsius. So if we're refilling it from over here, of course, at minus 30 degrees Celsius, you take a look at a isobar and see what corresponds that to 21 degrees Celsius, because the flight crew, we have another one, which is a transducer. The transducer always provides the corrected pressure at 21 degrees Celsius, okay? So that is the 70 degrees Fahrenheit, 21 degrees Celsius, which is the temperature that the transducer will provide the reading, okay, of the available oxygen to the system. And also we have, so here is how the masks, the flight crew mask, can be stored. Usually this is what we call a stowage box, and this is a stowage cup. Stowage cups are used whenever we don't have enough room for the masks, but they have a problem of contamination, okay? And we cannot test there is a procedure, which is the pre-flight test for the flight crew to determine whether oxygen is being provided to the masks. This cup, we need to remove the mask in order to test it. This one we can test without touching the mask. So I'm going to tell, not only for oxygen system, something like that, people. The fewer times one manipulates the system, the better. Okay, we have maintenance intervals which are established based on the safety assessment that we do, the failure modes and everything else. I'll talk it later. But so this is, nowadays, if you go to an aircraft, all of them are going to have like stowage boxes. So the mask is stored. We can test it with this little button here we'll have a flow indicator that the oxygen is being provided, and but we're never going to touch the mask, which is horrible. The more we manipulate an equipment, we add failures, okay, to the system which are not identified by the manufacturer, okay, whenever dealing the mask. So as I told, we have like a DOT cylinder. So usually they are, you can see, this is not really basic, but what I want to concentrate, oh, sorry. I want you to concentrate on is a Kevlar. This cylinder can be metallic, or as an evolution of the cylinder, more and more we're using composite materials for the crew oxygen cylinder. Why? First of all, it's far more, it's not as heavy. So a metallic, this is a 115 cubic feet cylinder. Okay, I can tell you that some aircraft that I work with, like the Lineage 1000 and the Global, they have this kind of cylinder to provide. Can be like 50 cubic feet cylinder, 77 cubic feet cylinder, 115 cubic cylinder. That depends on the supply duration that you want to provide. So we can have a metallic, or we can have composite. It can be Kevlar or carbon. Carbon is not only far more resistant, it's lighter than Kevlar, and more we're using carbon as well. Of course, there is a problem. It's far more expensive. So usually people stay in between with Kevlar. Okay, what we have to do with the cylinder is every 5 years, the cylinder needs to be like, it varies. So if you use a metallic cylinder, it's going to be, I'm going to give you an example. 115 cubic feet cylinder would weigh something like when it's fully charged, something like 8 to 9 kilos. A metallic fully charged would weigh something like 20 kilos. Okay, so weight is the greatest issue that we have on aircraft. When all of you start working, and I'm very glad that people are showing very interested. When all of you start working in the aerospace industry, you're gonna have people from weight. Okay, they're like little gremlins that come, like hauntings. Every day they're gonna come, and they're going like, they are like one of those demons that come every time to say, you cannot exceed this weight limit. So whenever we reduce something like 20 kilos or 30 kilos in a 1 kilo sometimes on a system, when you take the overall, is amazing. Okay, when we design the system, usually design the aircraft, usually it extrapolated, it exceeds 1 ton, okay, of what you're supposed to do. So we always have to have this weight reduction campaigns. So the Kevlar is far lighter. Okay, and right now the Kevlar has been added. So the metallic doesn't have hydrostatic testings, most of them. The Kevlar needs to have a hydrostatic test. It used to be 3 years, now it's 5 years. So every 5 years, we remove the cylinder and do a hydrostatic testing, okay, the supplier does it to make sure that the elastic properties, okay, are still part of the cylinder. So as I said, it's a 5 year, and every 15 years, you have to remove and change the cylinder. This is another cylinder, which maybe you have seen when you are on the aircraft. They're usually located in this is for the cabin crew to access. In the cabin, it's a portable oxygen cylinder. They're used for they are designed, they have to meet requirements for 2 flow requirements. One is first aid, and the second one is hypoxia flow requirements. So we have to demonstrate, especially for the cabin crew. EASA has been very, EASA is a very, I would say that EASA has a lot of far more stringent requirements, not far more, but more stringent requirements on as issue papers, and they call it CREEs, okay, certification reports that they come up with according to oxygen. As I noticed, far more than the other authorities. The other authorities are all concerned, but EASA has been very diligent on hypoxia and fire protection. So this portable is located in the cabin. Usually you have a minimum of 2, okay, according to the number. It depends on the number of passengers that you have on board, and they are distributed evenly. Usually they are located close to the cabin flight attendant seats, okay? And they have to be easily accessible, okay? So this one is used, sometimes you see movies that the aircraft is descending, people are not wearing masks, and the cabin flight attendant comes with that. No, this is only used for first aid. Of course, the aircraft is pressurized. Whenever someone has a cardiac arrest or needs some kind of supplemental oxygen, or after the depressurization event, when the aircraft is leveled off at a safe altitude, like 10,000 feet, the cabin attendant will come with this bottle in order to provide oxygen to those who are not able to don their passenger masks, okay? But this is only done after the aircraft is leveled off. Also, the cabin attendant can use that for self-protection against hypoxia. This, you can see, is the two masks. Here we have the passenger mask, which is the one that we are known for, and this is the flight crew mask. I have two examples of flight crew mask here. This is what we call an oral nasal mask. It's called quick donning because this harnesses here, they are inflatable harnesses. Nowadays, every single aircraft on the planet has these inflatable harnesses. So whenever we remove, like I said, we remove the mask from the stowage box by pressing these two red buttons, we remove the mask, the oxygen, there is a valve that flows part of the oxygen to the inflatable harnesses. They will inflate so that the donning of the mask is achieved within 5 seconds. There is a requirement that says that every flight attendant, every flight crew must don their masks and have them secured and providing oxygen within 5 seconds by using just one hand. That requirement is the 425-1447-C2, and it is demonstrated by a ground test. We sit each flight crew on the pilot position, full pilot, we call the 1P, the first officer, the pilot and the first officer, and we have to demonstrate that within 5 seconds, each flight crew will be able to don the mask using just one of the hands. I've seen pilots, they are really Jedis on crew mask donning because they do that in 1.5 seconds. Okay, but the mask is designed to facilitate that. Why do we have to test it if the mask is designed for the 5 seconds? Because the moment we install any equipment on the aircraft, there is a requirement, which is 1301, that says that we have to demonstrate that once installed, the equipment must function as designed. So that's how we do it. We can see the goggle here. Okay, so some come with the detached goggle, and this is for smoke protection. Okay, it's the protective film. So this is the inflatable harnesses. So this is to protect. So whenever we have an emergency, the aircraft, the depressurization, they set the mask to 100% oxygen, pure oxygen. Okay, if they forget it, the regulator itself has an automatic feature that will engage the 100% mode, because usually you can put a normal mode. The normal mode is whenever you have to save oxygen from the cylinder. So it mixes cabin air with pure oxygen. The 100% is pure oxygen. Okay, so you have, and you only, it's not a continuous flow. Okay, it's a demand flow. So whenever you put the mask will provide oxygen whenever we inhale and then we exhale. Okay, this oxygen. And there is a consumption curve. That's why the mask is called a TSO, Technical Standard Order, which is the minimum performance requirements. The mask will be designed to provide the required amount of oxygen flow at every single altitude for the flight crew to perform the required procedures. The passenger mask also provides the necessary required flow, but more for survivability of each cabin occupant. Okay, they cannot perform any like a fast process or something like that, any procedure, anything else but sitting and waiting for the aircraft to level off at a safe altitude. The flight crew, we all know, has to fly the aircraft and perform all the emergency procedures. Okay, so they need far more oxygen supply, okay, and I would say content than the crew. We also have, whenever you don the mask, there is a microphone, an embedded microphone on the regulator, and it can easily be activated manually. Okay, so the communication system is disengaged, and the aircraft communication system is disengaged, and the communication is done through the mask. Okay, or you can done automatically. The moment there is a switch. Okay, the moment, of course, this is the OEM has to decide. You want the automatic feature. The pilots love it because the fewer procedures they have to perform an emergency procedure, the better. Okay, so what it does is the moment there is pressure, the delta P of the oxygen flow in the mask will activate a switch that will immediately automatically engage the microphone. This microphone is used for external and internal communication. Okay, of course, that in an emergency like a depressurization or cockpit smoke event, the pilots are trained to do everything by heart. They memorize everything. Okay, but it's always good to have. So if there is a failure on the microphone, this is what we call a major event. Okay, so the loss of the mass communication system is a major event because they can still fly the aircraft, and it does not at all. It's an independent system from the flow of oxygen. The mask in the cabin is like we see here is there is this bag, and the mask is differently from the flight crew in basically two instances. Of course, there is no microphone, and also it's a dilution system. Okay, so the mask uses part of the oxygen, the supplemental oxygen that combines with the cabin air and provides the amount of necessary oxygen, partial pressure oxygen supply to each of the cabin occupants. So there are valves. Okay, I think that we have. You can see here there are 3 valves. Okay, on the mask. One valve is the inflow that comes directly from the oxygen source. We're going to talk about that a little later. There is the exhaust valve and the dilution valve. So when we inhale, we have oxygen. So the oxygen keeps on continuously flowing inside this bag. And people say, oh, but the bag is not inflating. There is no way this bag is going to inflate. And this is what the cabin occupants tell in the briefing before the safety instructions before the takeoff. Do not worry if the bag is not inflating. But since FAA has demonstrated about 70% of the passengers do not pay heed, do not pay attention to the flying instructions, okay, they start complaining that the bag is not inflated. This bag is never going to inflate. There is not enough energy or pressure to inflate this bag, okay? So it will inflate, not noticeably, but with the amount of oxygen necessary that will be combined with the cabin air, okay? Because we have a depressurization doesn't mean that we still don't have air flowing inside the aircraft. So the cabin air, the oxygen in the cabin air will combine with the supplemental pure oxygen, 100% oxygen, and we inhale, and when we exhale, these 2 valves are closed, and the exhaust valve exhales the CO2, okay, in the mask. Why do we have to have elastic band? because the elastic, whenever there is a depressurization, especially a sudden, like Fabio was telling about the system failure on the CPCS, the CPCS has a failure which is the most critical one, would be like the outflow valve fails open, for instance, okay? That will lead to a cabin altitude rise. Aircraft usually fly at, usually the cabin altitude is maintained at 8,000 feet, okay, at 41,000 feet. Let us imagine we have a failure from the outflow valve or failure from the back, whatever. That cabin altitude will start rising, okay? But it's a slow rising, okay? It gives time, first of all, to alert. There is an indication system, alert system to the pilots that when before he reaches 10,000 feet of cabin altitude, the pilots will don their masks. So the cabin, and you start descending the aircraft. The cabin altitude will start rising, keep on rising. Before he reaches 15,000 feet, the masks are automatically deployed. So these masks will deploy. So you see like the deployment of the masks. When you travel, you see like the videos, okay? In case a pressurization happens, the unlikely event of a pressurization change, the mask will deploy. Stay calm, pull your masks and breathe normally. Okay, you're not gonna stay calm, you're gonna pull the mask, okay? But what you have to do is you have to place them over the mouth and nose, and you have to put an elastic band. The reason is if you don't put elastic band, you're not gonna, because you're gonna inhale part of the oxygen and you're gonna pass out, especially if it's a sudden decompression. If you're flying at 41,000 feet or 43,000 feet and there's a structural damage, okay, the transient that goes from ambient pressure to cabin pressure is almost inexistent. There is no slow cabin altitude rise. It's instantaneous. It's 0.1 second for that for both pressures to equalize. A lot of people may pass out, okay? That doesn't mean you're going to have fatalities, and I'm going to explain to you later. So what I'm telling you is you have to put the band because we already have some kind of oxygen storage in our bodies. So when there is a decompression, we use the oxygen partial pressure in our lungs, our alveoli, okay, in order to process that and send to the brain. If we don't put the elastic band, we're going to pass out, okay, because we're just going to have that amount of oxygen, and then we're going to wake up again. I'm going to breathe in and we're going to pass out. So the elastic band is mandatory, okay? So I'm going to come back to the system. So this is the mask. As I said, it's completely different from this mask. The main feature, hypoxia and fire protection, okay? Hypoxia protection, fire protection. This one, only hypoxia. Hypoxia, as you know, people, is the low content of oxygen, okay, in our lungs, so that it can be fatal. I'm going to give you something like above 25,000 feet. If the aircraft remains above 25,000 feet for more than 2 minutes, which is not allowed by a certification requirement, you have to demonstrate that the cabin altitude will never be at 25,000 feet for more than 2 minutes. Why is that? Because the survivability at 25,000 feet about 2 minutes, okay, for the oxygen system is fatal. The oxygen partial pressure, if you are exposed to it's something like 22 to 25 millimeters of mercury of oxygen partial pressure, that is absolutely fatal for more than 2 to 3 minutes. So you're going to have brain damage and fatalities. That's why people are worried about, oh, but the masks do not deploy. Don't worry about it. If there is a failure of the passenger mask, the passenger oxygen system, about the mask are not deployed to the cabin occupants or just few of the occupants, the aircraft will start descending. And as we descend, the lower the altitude, the higher the partial pressure, the oxygen partial pressure, our organism will immediately, it's not like a sudden death, okay? You pass out and you start recovering as the aircraft descends. However, we always have to have the oxygen masks, okay, because you're designed to do that. So basically, this is the distribution system. We have flex hoses. They can be high pressure hoses like this one, which is a metallic hose. This is I'm not mistaken, is stainless steel braided, okay? But it can also be low pressure hoses made of rubber, something like that. This is the oxygen pressure transducer. As I said, it's linked to the oxygen cylinder. So this is over here. So the oxygen cylinder has a pressure transducer, which corrects the pressure according to 21 degrees Celsius. That can be done straight from the transducer, or it can be done through the interface with the avionics system. And it provides an indication of the amount of oxygen to the flight crew that they still have available. And whenever we reach a minimum amount of oxygen for the flight crew, we have what we call a crew alert system, a CAS message, which is usually caution, that says, look, you have enough oxygen just for certain amount of, you have the minimum supply of oxygen required. So if the aircraft is flying normally, the CPCS is functioning, the aircraft will have to descend to 10,000 feet, even if it's okay, so easily deviate, because if we combine that with a flight smoke event or a pressurization event, and we have no supply of oxygen to the flight crew, this is a catastrophic event. We know the flight crews are passed out. If you remember what happened in some years ago with that aircraft that was flying from Cyprus to Greece, and there was a pressurization event, and the flight crew, instead of following the AFM procedure, decided to troubleshoot. Okay, they did not understand. It was a very slow cabin altitude rise, and hypoxia cannot be determined. You cannot feel you're under hypoxia. If you go to a hypobaric chamber, okay, a pressure chamber, you see that people have no idea that they are under hypoxia. Okay, so they passed out. The cockpit door, because of security consideration, was locked. There was no way, and unfortunately, you saw there was a catastrophic event because the passenger mask dropped, but there was no ECS. So we went, the autopilot keep on flying at 41,000 feet. There is no CPCS or ECS. It's hypothermia, okay, that ended up killing everyone on board. So whenever there is a depressurization, and this is the transducer will provide the necessary amount of oxygen, okay, that will provide an indication of the amount of oxygen that there is in the cylinder for the flight crew to meet the requirements, okay, which is a 2-hour oxygen for each of the flight crew. This is a low pressure switch I just installed here in the low pressure lines right after regulator. As I told you, 1850 psi. After regulator goes from 65 to 80 psi. If this pressure if somebody shuts down the regulator, this line will be depressurized. Okay, so this is also indicated to the pilots. Why? Because the transducer, this is very erroneous. That happened once so this is one of the evolutions. There must be an indication on the low pressure line, because there was a case of an aircraft that the maintenance team shut down the cylinder. Okay, when you shut down the cylinder, all this pressure over here, this line, which is constantly pressurized, okay, was depressurized. But because there was a transducer and the pilots decided not to follow the FM to, like I told you, to test the amount of oxygen. In fact, they did test, but there was very little oxygen so they were mistaken. They were fooled by thinking that there was oxygen in the lines. So what they did is they flew, okay, with this oxygen cylinder closed. The transducer was telling them, look, there is enough oxygen in the cylinder. But the low pressure switch, there was no low pressure switch here, you can see in the line. This low pressure switch was inexistent. So how the pilots knew? One of the co-pilots decided to, because of FAA regulations, operational requirements, one of the flight crew, this is FAA, one of the flight crew members leave the duty station, like go to the cabin, okay, the other one has to don the mask. When he, above flight level 250, when he donned the mask, he realized there was no oxygen available. because there was no oxygen flowing through the mask, so they descended. So now we have to have a low pressure switch in the line to detect the low pressure in the low pressure part, okay, of the oxygen system distribution. So this low pressure switch will also send a CAS message, but this one is a transducer. So and this one is a discrete signal. This is a mechanical switch, okay, that will send an electrical signal to the avionics to produce. And also you have the pressure gauge, okay. Nowadays nobody wants, I always want to put a pressure gauge in the cockpit, because it's not only a redundant system, it's also a dissimilar system. This is something it's good for you to understand. Redundancy doesn't give complete protection. Sometimes you have to have dissimilar equipment. This is a transducer, electronic equipment. This is an analog equipment. If you have that on the cockpit, you can dispatch the aircraft if there is any issue with the transducer, for instance. And so you also have, I forgot, distribution lines. You can use capillary lines. Oh, they are very light, they're very good, but they're horrible because they break easily. So if you're going to ever design a system with capillary lines, install it in places where people do not step on, where have very little access, because they break easily, and when they break, they leak all the oxygen, okay, in the compartment. The passenger oxygen system, as I said, so we talk about the gaseous, called gaseous system because the source of oxygen is stored in gas. And we have the chemical system. The chemical system, of course, that the result is gaseous oxygen, but it's stored as a chemical core, okay? So there is a chemical core, okay, inside this COG, it's called chemical oxygen concentrator, or sorry, it's not concentrator, it's my mistake. It's chemical oxygen generator, okay? I'm gonna correct that. This COG is stored, okay, in the what we call the passenger oxygen box, along with the masks. You're never going to see that, because when you get on the aircraft, you see what we call the passenger service unit, where you have the microphones and the chimes to call the flight attendant, the lighting, and that little thing that I know that Fabio and I, we hate, which is the little, what we call the Gasper eyeballs, which is for individual ventilation. That is a horrible thing, because the Gasper is for individual, and everybody closes that. And whenever we have like a smoke penetration event, that Gasper valve steals a lot of, let's say, it robs a lot of pressure differential that we need in case of we need to dump the smoke that exists, or prevent it from presenting. So from penetrating the cabin, the occupied compartments. So we have the COG and the masks. So what's going to happen is, whenever there's a depressurization system, there is a depressurization event, sorry, there is a altimetric switch that is going to read the cabin altitude rise. Before you reach 15,000 feet, it will automatically send a signal and open the doors, okay, that you have in the PSU. The masks will deploy. And why do we have to pull the masks? We have to pull the masks because the moment we pull the mask, we release this little pin that exists here. This pin, when it's pulled, so the mask's deploying, there is no oxygen flow. The moment we pull the pin, there is like a little spark, a small, like a smoke spark, sorry, fire spark, okay? It's an exothermal reaction happens here. It adds a lot of heat to this system. It's an exothermal reaction. So the sodium, I forgot, chlorato de sódio, which is a sodium chloride, which exists in here, along with the energy, with the source of heat, will, as a stoichiometric reaction, it will produce oxygen and salt. So the core will melt into salt, kitchen salt, the one we have, sodium chloride, and will also produce oxygen. This is there is a requirement that shows that the temperature here on the core can reach, I'm not kidding you, can reach something like 250 degrees Celsius, okay? So we have to make sure that this heat, it's a heat transfer through radiation. It's segregated and separated from lines and from kind of oxygen and so forth. So this is designed so the oxygen flows in here. When you pull the mask, you pull the pin. Even if you're not wearing the mask, the oxygen will flow through all the 3 masks or 2 masks, whatever configuration you're using, and it will provide a necessary amount of oxygen supply, supplemental oxygen that, as I said, will mix with the cabin altitude, with the oxygen inside the cabin altitude air, and will provide a necessary amount of oxygen for hypoxia protection. Okay. Usually these, and this is why I'd like to say, these COGs usually provide something like 22-minute. You can provide like a minimum, the requirement says you have to provide a minimum of 10-minute oxygen supply. The requirement for transport categories, okay, transport, I'm not talking about corporate jets, transport categories, says a minimum 10-minute supply to each cabin occupant. These COGs can provide 12, 14, 22 minutes. Right now, we have more and more providing 30 minutes, 45 minutes, an hour, okay? But then depends on the size, and of course, it adds a lot of thermal load to the cabin, okay, if you're flying for a long time. So this is a source of thermal load. I've always worked with 14 to 22 minutes of oxygen supply. So let us say that you're flying in a place, the operation is like flying the Himalayas or the Andes, where you cannot descend immediately to 10,000 feet. So the aircraft operation says, look, I'm going to fly. No, I'm not going to fly in any kind of mountain range. The mountain clearance is not going to be an issue. You put like a 12-minute COG, because in less than, I'm telling you, in less than 10 minutes, the aircraft is going to descend to 10,000 feet. Sometimes it descends in 4 minutes. It depends on the kind of failure. If it's structural damage, if it's a system, if it's a CPSS system failure, if you have 1 engine or 2 engines, that depends on the rate of descent. I'll add. But you always look at 12 minutes. If you say, no, I'm going to fly in the Himalayas. I'm going to fly, the operator says, I'm going to fly in the Himalayas, or I'm going to fly in the Peruvian or Chilean Andes. So we put a 22-minute, which is the amount of time that it needs to descend to a safe altitude before mountain clearance. Okay. So I'd just like to say that basically for the, I forgot to put, I'm going to add, so you have the COGs, the passenger masks, the passenger oxygen mask assembly that we say that we put everything in the that, and I forgot to add, I apologize for that. I had the picture and I just realized I do not add what we call the altitude switch, which, as I said, is the component that senses the altitude change, cabin altitude rise, and before it reaches 15,000 feet. So remember, for the flight crew, 10,000 feet, they need to have supplemental oxygen. The cabin occupants, before it reaches 15,000 feet. The masks can be deployed automatically through the altitude switch, so the pilots do not have to do anything, or it can be deployed manually. Okay, so at the discretion of the pilot, he deploys, there is a switch that he presses, or there is a knob that he, according to the system architecture, okay, but usually it's a button that you press it, and the manual system overrides. How is it deployed? If it's a chemical system, it's electrical. Okay, so you have here latches, electrical latches. They are provided for about no more than 5 seconds. Each one is like something like 0.15 ampere. Okay, that provides in electrical harnesses that run and provide necessary electrical energy just to open the door. So there is a latch. It's a solenoid. It's a solenoid that whenever the current goes through, it opens, and the masks are deployed by gravity. Okay, the masks are deployed by gravity. In the gaseous system, it's good that I say here, in this gaseous system here, if the passengers, the cabin occupants also use a cylinder source, okay, it's the pressure differential that will make the masks deploy. So whenever there is a cabin out to rise, there is a valve here that will open, oxygen will flow through the tubings, okay, and they will open by pressure differential. If there is a chemical system, we need to have electrical harnesses designed, assigned, just for the electrical latches to be provided the required amount of electrical power input, okay, in order to open the doors. The manual deployment is the same. What the manual deployment does is through a button. The button activates a different electrical source, usually essential. We have on the aircraft DC buses and essential DC buses, okay? The passenger oxygen system is usually, the oxygen system usually linked to essential DC buses. Essentials are the ones that will be operative, will be operational in case of an emergency event. So usually we put the automatic on one DC essential bus in order to segregate, and the manual on a different essential bus. So the source of electrical power output is different according to auto manual, but the functionality, the idea is the same. You will provide an amount of energy, electricity to that. This is just a little, I would like to say, O-box architecture. This is something that is very much used in military aviation. And why? Because we don't want to have cylinder, oxygen cylinder sources, oxygen cylinders, okay, on an aircraft, on a military aircraft. Okay, because of explosion, because of if it's hit by a bullet, something like that, you're going to have some kind of what we call a plastic deformation and source, an oxygen source, which combined with the fire. So what we do is the O-box is linked to the bleed system. There is a port on the bleed system, okay, that can be the same port that comes from the pack or something like that. It filters the bleed air. There is a valve. This valve goes for solenoid. Basically, what we have is the separation of the oxygen from the nitrogen. Okay, and that when this phenomenon occurs, the oxygen is finally provided. There is a planing to balance the pressure, and the oxygen is provided directly to the pilot mask, okay, in case of military operation. For military operation, we don't have the stringent requirements for the civil aircraft at all. So there is no need. First of all, the aircraft is not going to fly as high as the civil aircraft. So the amount of the percentage of oxygen that is provided to the flight crew, to the pilots in the military aircraft, does not meet the same standards as the civil aircraft. And that is the problem with O-box being used in civil aircraft. At high altitudes, we need to have a backup system, okay? First of all, because there is a need to warm up the system, okay? Whenever there is a depressurization, so the pilots, the civil aircraft pilots will activate the warm up, the O-box, but they will have to use they will have to be provided gaseous oxygen from cylinder sources until they reach a certain altitude, when they can start using, okay, the O-box. That is very, authorities, I myself have never worked with a Part 25 aircraft, or like a transport category aircraft that uses O-box at all. I know there are some corporate jets are starting to use them, but still a lot is required to demonstrate certification for that. Authorities would ask a lot of data, validation, analysis, flight tests to demonstrate that the not only the flight crew, but also the cabin occupants would be protected. The advantages of a no box: weight and system architecture. We eliminate all those lines and cylinders and transducers, everything like that. The disadvantage, all of a sudden we have the oxygen system. There is a requirement, there is an SAE standard, ARP 4754, that talks about, one of the things is how the systems are interfaced. The oxygen system is considered an independent system. It does not interface with anyone. It does not interface with CPs. The functioning of the oxygen system does not depend on the functioning of the other systems, okay, at all. The moment we have oxygen being supplied to that, okay, this is what happens we suddenly have interface with bleed system. So the failures in the bleed system will also affect the failures in the oxygen system. So design, installation, safety issues. How do we determine what system architecture we're going to use? Well, it's basically what kind of aircraft you're going to fly, what kind of requirements you're going to comply with. Like if we're going to fly a transport category 121, usually go for gaseous systems for the flight crew and chemical systems on the cabin. But it depends on how long you're going to fly. If you're going to fly ETOPS, which is one engine extended operational for the aircraft, it's like when you have a single engine failure, we cannot find a deviation place within an hour. We had like a 2-hour deviation, a 3-hour deviation, like 270 a minute deviation, 120 minute, 180 minute deviation. Sometimes and we cannot descend merely to 10,000 feet. And the performance group says, look, you cannot fly for 2 hours at 10,000 feet because of the drag, because of the fuel critical scenario. You have to fly at 15,000 feet. You have to fly at 19,000 feet. So the chemical oxygen generator is not enough. So you need to supply oxygen, imagine, for all the cabin occupants for 2 hours. Okay, not only for the flight crew, for the cabin occupants. We usually use the gaseous system. But usually if it's not ETOPS, and if it's ETOPS, the emergency at single engine combined with the pressurization, for instance, can be done, because you can do single engine and the aircraft is still pressurized. But if you combine single engine with the pressurization, the aircraft has to descend to 10,000 feet. And but if you have to fly for 2 hours, the fuel may not be enough. Okay, so the fuel critical scenario says I have to fly at 15,000 feet. And then we have to provide energy. Okay, we have to provide oxygen. Okay, to everyone for 2 hours. So we go for a gaseous system. The sizing of the crew oxygen system is to do the oxygen flow requirements for the flight crew and the passengers. So the flight crew needs 2 hours of oxygen with 10 minutes for emergency, another 110 minutes for reserve. The cabin occupants, a minimum of 10 minutes. Okay, so well, how are we going to do that? So we get the CPCS critical failure leading to the fastest cabin altitude rise. So let us say, what is the most critical failure mode that exists in the CPCS DCS that will lead to the fastest cabin altitude rise? And that is how we have to go and come up with a critical aircraft emergency descent profile. We start showing that the amount of oxygen necessary for that critical emergency descent profile. As I said, is the aircraft going to operate ETOPS or not? It's going to operate where you have mountains, okay, mountain clearance and supply duration requirements. The supply duration, I can say the 121 says that a minimum of 10 minutes to each cabin occupants. The FAR Part 135 says a minimum of 30 minutes to each cabin occupants. Okay, or from 30 minutes to 1 hour. So that's why these corporate jets, like you see, the Praetor, the Legacy, the Global, the Gulfstream, they all have gaseous systems for cabin occupants, because there is no way that we provide the amount of necessary for 30 minutes or 1 hour using chemical oxygen generators. Also, the system location on the aircraft. This is one of the greatest fights that exist. People fight for a place on the aircraft like they fight for their lives. I've seen people yelling at each other because you cannot put it there because they have this is my avionics. This is not, so this, I cannot place it there because I already have the wastewater system. The oxygen system, you have to remember that, needs to be segregated and separated from flammable fluids and from ignition, electrical ignition sources, completely segregated. The best way is to have a dedicated compartment to that. Sometimes we don't have it. I've worked with aircraft that we can put in the pressurized compartment. Sometimes there is no room in the pressurized compartment. So what we have to do, put in the unpressurized compartment, like one of the aircraft that I worked with. Unpressurized compartment, a lot of issues. The system installation, you just said, you have to do a zonal safety analysis. Okay, you have to demonstrate that every system does that. Okay, it's not only oxygen system. Every system is a part of the 1309. You have to do a zonal safety analysis to show that where you install the aircraft, it does not pose as a hazard to the other issues or to itself. Okay, so segregation, minimum clearance from fluid, flammable fluid, and ignition sources. Air ventilation design. If you put in the pressurized compartment and all that aircraft, all that oxygen content is discharged, okay, you may have an oxygen enriched atmosphere. That is an issue, a big issue, because whenever you have an oxygen, what we have 21% of oxygen content in the ambient air. Transport Canada says anything above 23% of oxygen concentration is already a fire hazard. So either we put the oxygen in a place where you have no ignition sources, or you provide some kind of ventilation system to dissipate, first of all, to dilute and dissipate that oxygen that is done. I'm going to give you like an example on the, if you remember, I'm not going to go back a lot. If you remember what we had in the cockpit, the cockpit has the stowage boxes inside the cockpit. If one of those tubings or hosings, they have a rupture, that oxygen will immediately flood the cockpit. So what we have in the cockpit, we have electronic equipment, we have ignition sources. So what we have to show is demonstrate that the oxygen concentration will be instantaneous, but the most critical ECS flow will provide the necessary amount of air to dilute that oxygen and not pose as an oxygen as a hazard concentration. EASA says, okay, very good, I love that, but now you have to flight test to validate this model. Okay, so the zonal safety assessment, ambient design, oxygen lines, the way they route them. Oxygen loves electrical connectors. It's a law that we have to break. We have to stop them. It's like you have a marriage that you're never going to allow somebody to marry someone. So stay away. Oxygen source lines, everything must be kept a minimum of 6 inches away from any oxygen source. Okay. We also have the proof and burst pressure. We have to demonstrate through a requirement that what is the maximum ratio of proof and burst for the hoses. Overpressure discharge, if there is like a rise in the temperature in the vicinity of the cylinder, we're going to have a rising temperature, a rising pressure. That pressure must be discharged outboard, overboard the aircraft. So there you have a little orifice on the fuselage that exhausts all of that. And contamination. I'm going to tell you, there is an accident that happened once that the guy was going to over 707 of the no longer existent airline called Varig, Brazilian Varig. It was a brand new 707. That was in the 70s. So they were about to refuel the cylinder in the hangar, and the personnel, the staff, decided to refuel the cylinder, and the hose that is used to connect to the supply panel was dirty, was contaminated, was a little bit of grease and dust. So you have, and then they did something called adiabatic compression, so that the heat was too much. There was dirt, which is the fuel, heat from the velocity of that, and oxygen. The whole aircraft burned. There is no way you can control an oxygen fire. You can control like an example, fire on the engine is considered a major event. Why? because you can suppress it. If you cannot suppress the fire in the engine, then it's catastrophic. Fire in the cargo compartment is considered major. Inability to suppress that fire through the agents from the halon, for instance, is considered catastrophic. There is no way you can control an oxygen fire unless you close the source. Okay, so also you have to take care of, like, every system equipment. You're going to qualify, demonstrate equipment qualification for temperature, humidity, UIS, pressure variation for that equipment to be installed in that area that you chose. Like Fabio said about the avionics cooling. So the category for temperature goes up to operational, like say 70 degrees Celsius. I cannot put an aircraft on oxygen cylinder in a compartment above 70 degrees Celsius because it changes material properties of the cylinder. Okay. And also the refilling of the cylinder and maintenance accessibility. Maintenance, we always tell you, we always forget them. Never forget the maintenance people, because they are the ones that are going to have accessibility. Sometimes, like Fabio said about the pre-cooler, one of the worst places for maintenance is pre-cooler and engine and valves. So you have to try to find a place where it's easy to access, okay, easy to perform all the necessary maintenance procedures that are required, okay, to do, like in a certain time interval. So the refilling of the cylinder can be done. I've worked with aircraft that it's done through a fuel port, okay. Others decide not to have the fuel port because they have the capability of removing the cylinder, charging the cylinder remotely, and then putting the cylinder back. Okay, so it varies. Sorry. About the design installation issues, as I said, also you have the selection of the mask, as I told you. What crew mask I'm going to use, the continuous, a demand, or pressure demand? That depends on the aircraft ceiling operation. If you're flying a flight level 400, demand. Above flight level 400, pressure demand. Below, you can use a continuous mask, but still protected for hypoxia and fire protection. Like I said, it's a protected breathing equipment. TSO. TSO means technical standard order, which is the minimum performance requirements that the equipment has to demonstrate by the supplier. It's called C99 for the mask for the fire protection. And the mask must be individual, independent on operation and function, which means a failure on the pilot mask, on the function and operation, cannot affect it has to be independent for the co-pilot. Masks, passenger mask can be TSO, Alpha, 64 Alpha, or 64 Bravo. Okay, the Alpha immediately complies with 1443C. The Bravo has a weight benefit, but you have to demonstrate compliance with what we call equivalent level of protection. Why? Because the Alpha complies with the flow requirement of the requirement, or the flow supply of the requirement. The Bravo provides less oxygen than the 1443C, but still provides hypoxia protection. So you need to write an issue paper and demonstrate that through laboratory data, which is more than available. This is no news. All the aircraft nowadays that I know, the Embraer E2, the Airbus, the C-Series, they all use TSO 64 Bravo, which provides enough oxygen, what we call for the blood saturation. Okay. We also have to talk about PRA, particular risk analysis. It's another 1309 requirement, like the safety analysis, which says, what does the PRA? It says that a failure in one system cannot violate the independence with the other systems. So if you have like an engine non-containment, the fan blade goes out and presses the fuselage and opens a hole, okay, that cannot stop the oxygen in the cabin from being supplied, provided. Of course, we remove the crew oxygen system from the debris angles. We're not going to have a debris, okay, close to the flight crew, but the cabin is not good to do. It's not possible to do it. So we have to say, if a supply line is severed, or electrical harnesses is severed, we have to provide redundancy so that all cabin occupants are affected, so that the supply is not affected. We do, like I said, the hydrostatic tests, the DOT, destructive and non-destructive tests, and catastrophic fire because of oxygen-rich atmosphere. This is the greatest issue nowadays. Authorities have been extremely concerned with oxygen fire. Whatever articles you read, people, on oxygen fire on the aircraft is very good for you to see how you comply with that. Basically, we demonstrate the oxygen is isolated, segregated, and the oxygen concentrator leaks because of a system failure will not pose a fire hazard, okay, to the aircraft. This is also what we do about system. Every system does that. Aircraft is a function hazard analysis. It's when the function fails because of the function stops, when the system stops providing the required function because of a system failure, okay? I can give an example of an oxygen. Loss of oxygen supply, major event. So we can do it no safety, minor, major, hazardous, catastrophic. So the loss of the oxygen supply is major because we still have the ECS and CPCS operative. But if we combine the loss of oxygen, loss of crew oxygen supply with depressurization, or we combine with fire smoke event, it's catastrophic. Okay? For the passenger oxygen system, there is some flexibility on working because of the ability to descend to 10,000 feet and the oxygen partial pressure, so we can put a hazardous event, the loss of oxygen supply, cabin oxygen supply, combined with the pressurization. The reason is because the oxygen partial pressure will not remain at critical levels. The aircraft will start descending. And the moment we go below 15,000 feet, our metabolism is capable itself of recuperating, okay, the amount of oxygen that we need. So as I told about fire event, oxygen system requirement evolution, this is a fire event that happened. I'm going to tell you what happened. This is a FedEx Boeing 767 that was on ground, thank God. And this is an Egypt Air Boeing 777 that was taxiing, okay? What happened is, they use, nowadays it's obligatory that no metallic hoses, remember I told you about the metallic hoses, they are stainless, that they're steel braided, they are conductive, okay? If you use rubber noses, I mean the roses, they are not metallic, these hoses cannot contain any metallic part and they need to be grounded, okay? Because these both accidents happen because there was oxygen in the lines. There was a short circuit, okay? And the short circuit, the electricity found its way through, there were springs. So in order for the flexibility, the low pressure hoses had metallic springs inside it. So of course, the electricity will find a way to ground itself. The hoses were not grounded, okay? So, and were not, so what happened is there was oxygen, electricity, heat with the fuel, the fire. Look, this is what happened on ground. You can see here the rope. This is through how they opened the window, okay? And they exited through they were preparing for the pre-flight. And this was like with almost 300 passengers on board. While it was taxiing, smoke got in the cockpit because of the same event, short circuit, oxygen in the cabin. Imagine if this happened, both accidents happened in flight, it would be a complete loss of the aircraft and the death of all the aircraft occupants. It happened on the ground. The Egypt Air was able to evacuate everyone within, I mean, they opened the doors and evacuated while on ground. And here the flight crew escaped. This is a FedEx. Okay, so it's a cargo airplane. They escaped through the side windows. Okay. We have oxygen fire protection that needs to be analyzed. I said the oxygen leakage analysis and air dilution design. Security considerations. This is, we cannot use the COGs in laboratories anymore, okay? Someone found out that their bombs can be built, okay, through COGs. So if it's not obvious, okay, that someone is manipulating or tampering with the COGs, okay, opening the door, I told you, like open the door and start manipulating the COGs and the masks, if that is not visually obvious to the cabin crew or anyone, okay, they need to use COGs. They can be used, but we have to show detection system and so forth. So what did the operator start using? Gaseous system, so mini cylinders in the laboratories. The laboratory has many cylinders that provide gases. Why? Because someone can lock himself in the laboratory and there is no way that we can see what the person is doing. If somebody tries to tamper with the smoke detector in the laboratory, it's a continuous bit. So you will immediately tell the pilot, okay, because it's a continuous bit, if you remove the smoke detector, there is a signal that is sent as if there is smoke in the laboratory. That doesn't happen with the COGs and the passenger masks. There is no detection. So what they prefer, they put a mini cylinder in this for security considerations. This is a mask that is used for fire combat. Okay, it's also called a PBE, a protective breathing oxygen. Protective breathing, but it's a smoke hood and it's for fire combat. Okay, this is used by the cabin occupants, and I hope none of us will ever see a cabin occupant wearing this, okay, while we're flying. And a flow requirement, so this mask provides oxygen and smoke protection when directly combating a fire, like on board, okay, in the cabin, in the laboratories. Okay, so they use the fire extinguishers, and it provides for about 15 minutes of oxygen for the fire combat, this is also a TSO equipment. And the flow requirements compliance, as I said, hypoxia protection for system failure, like a CPCS, the cabin O2 rise is very slow. The structural damage is instantaneous, okay? So I also put like something in Lithuanian questions. Thank you for your attention, first of all. Thank you, everyone.
Yeah, thank you, Filipe, for a very nice presentation. So, students, it's question. You have questions?
Where does usually the containers of oxygen is stored in Embraers? In which part of the plane?
Where the cylinders are stored?
Yeah.
Okay, so that's a very good question. So this, as I said, the crew oxygen cylinder, let us talk about crew oxygen cylinder because they're always gases, okay? So the cylinder is always has to be installed on segregated or dedicated compartments, okay? We must segregate the oxygen cylinder not only because of, I can give you an aircraft. I'm gonna give you the name of the aircraft, but I'm gonna give you. There was an aircraft that I worked, that the oxygen system compartment, the oxygen cylinder, was installed in a dedicated compartment adjacent to the forward cargo. But there was a firewall, there was a panel, was a firewall, and it had a dedicated ventilation system from the underfloor ventilation. So there was a flap valve when the aircraft was the underfloor, the ECS was flowing, it would open the flap valve and it had an orifice that would get rid of the air in the case of leakage. Most of the times you want to have it very close to the flight crew members. So usually it's located under, most of they are very close to the cockpit, okay? The reason is we have to reduce the length of the hoses and the lines that lead to the cockpit. First, because of pressure drop. We don't want a lot of routings and not only dynamic, but local pressure drops. We want to eliminate that. Second is something that oxygen leakage always occurs in the fittings. So whenever you have the threads, the fittings of either the aluminum tubings or the hoses, this is where the oxygen will leak. So the fewer the fittings, the better. Okay. So most of the aircraft that I worked with, the crew oxygen compartment, the crew oxygen cylinder is along with the regulator, the transducer, and the installation itself is located very close where you have the you have in the cockpit. There is one aircraft that I worked that the cylinder was located inside the cockpit. Okay, it's very good for the pilots to determine whether there is oxygen or not. On the other hand, you have the issue of oxygen leakage. So wherever, it's a very good question, wherever you install the aircraft, the cylinder, you have to, the requirements are the same to demonstrate compliance, but how you demonstrate compliance. And I'm going to give an example. Pressurized compartment. If you put your cylinder in a pressurized compartment, isolated, whatever, you have to have some kind of ventilation system designed in case of oxygen leakage. Okay. If you put in the unpressurized compartment, the leakage is not really an issue, provided you have no external ignition sources close to that. Because we know in an unpressurized compartment, the temperature would be very close to the temperature envelope at high altitudes. So there would not be, the fire event, the fire hazard is lower than if you put in an ambient where you have controlled temperature because of the ECS. So I'm just want to tell you, above 23% of oxygen concentration in confined, this is a Transport Canada for confined atmospheres. They say that above 23% of oxygen, not only will the materials that do not burn at certain temperatures, you're going to decrease the temperatures that certain materials can have auto-ignition. And second, the energy, at oxygen-rich atmospheres, the fire propagation rate is like exponentially faster than we don't have oxygen-rich atmosphere. This is exactly what happened with the Swiss aircraft that was flying from New York to Geneva, I think, and to Zurich, and it had to come back. The reason is it breached oxygen lines, so the oxygen fueled, okay, the energy necessary. So there is no way. So usually you put in, you always have to think about segregated compartment. If not possible, segregated compartment, separate from what we call electrical equipment free environment. There is no ignition sources nearby the cylinder or itself. So it depends on where you're going to find room to install, but you also have to make sure that it complies with the requirements. Did I answer your question?
Yeah, thank you.
Oh, my pleasure.
Okay, thank you. I personally remember one joke with oxygen generators. I got one generator after check from aircraft maintenance, and we did the experiment for boiling water.
Yeah, that's very good. Yeah,
good heating source, so you can prepare hot tea in winter.
Yeah, no, it's true. The radiated heat transfer that comes from that is extremely high. There is a requirement of FAR 25-1450 that specifically says that the temperature can never exceed more than 100 degrees Celsius at a certain distance from other equipment. So what we have to do is show also something else. The oxygen system, and what everyone needs to understand, we never work alone. So if the oxygen system is located close to ECS ducts or the interior panels, whatever, there is something that is very stringent, which is flammability requirements. Okay, we have to demonstrate that equipment, that duct or equipment or component that is close to the generator is not going to pose as a fire hazard according to flammability tests that we have to demonstrate. Okay. But it's good that you use that, because I also did a COG test once okay, and we wanted to. It was very cold. I mean, I worked in a laboratory that the thermal sensor was broken, and it was in Hartford, in Connecticut, and there were a lot of COGs available. And I said, why don't we just start operating them so that we can warm up the ambient? Okay, the guy next to me was not very, he had no humor. So he said, "You're not supposed to do that. You want to kill us all?" I said, "Okay, no, I'm just kidding." So I prefer, but you can heat up the ambient. So you can just imagine an aircraft with 300 aircraft, if it's chemical generators, and you have a depressurization event, it takes like 22 minutes or even 12 minutes to descend. The amount of heat transfer, the heat load that each generator will add to the ambient is pretty high.
If the COG is located in the panel over your head, where there's like a buttons and the air ventilation system and other stuff, does it, so as I understand, the oxygen can't be really close to the like electrical sources or something like that, but the passengers' masks with the COGs are located like very close to it.
This is an excellent question. Another second excellent question you did. Whenever we show, we have to demonstrate segregation from external source. As I said, you have harnesses and the electrical latch. So let me give you, first of all, let us think about these electrical harnesses that provide the power and the voltage and the power output necessary for the solenoid to open, and so allow the door to open and drop the mask. Okay. So that amount of electricity that is provided is momentaneous. It does not last for more. So the DC essential bus will have some kind of, it's not a latched situation. It's going to provide for a certain amount of time, can be 5 seconds, 10 seconds, and then the electricity will be discontinued. Okay, so there is no more electrical source, okay, on that latch. So the moment you pull the mask, okay, the oxygen starts flowing in the mask, that electrical harness is no longer providing electricity, and that has to be demonstrated through design. Okay. Second, as you said, you have a lot of like the chimes and the lightings and the microphone, and also the fasten seatbelt and no smoking signs on the whole PSU. That must be demonstrated that, first of all, the power output, those are usually not very high. They're very signal. They're just what we call signal cables. Signal cables are not something that you have to be worried about the power outputs, okay, like power cables. The power cables are located distant from usually from the PSUs. But you're right, you have to demonstrate that those electrical wiring and everything, and that is demonstrated before you put on the aircraft. They are absolutely segregated. When I told about the qualification, when you qualify the system, okay, for UIS, EMI, power input, voltage output, everything else, that needs to be demonstrated with the oxygen flow or not. So they will not pose that little, there will not be any kind of short circuit that will damage. Second, whenever there is a depressurization event or emergency event, most of the non-essential equipment, like the screens or what we call the IFE, the flight entertainment, okay, individual flight entertainment, everything is shut down. Okay, everything in the aircraft is shut down. We only have essential equipment operating, okay, in order to provide the necessary systems in case of an emergency. So anything which is non-essential is shut down. That doesn't happen with the PSU because you're going to have the same signal that makes the aircraft, the passenger masks drop. Will turn on the passenger seat belts and fasten the seat belts and no smoking alerts, okay, in the PSU. But that power output does not pose a hazard, okay, does not constitute a fire hazard to the oxygen system itself. And the oxygen system is isolated. The flow goes through the hose, okay, directly to the mask. And you also have, remember, you have the ambient air. So that oxygen is being diluted with the ambient air. And the COG is, the chemical generator is what we call hermetically sealed. Okay, there is no way. There is a wearing. If there is a wearing, there is a way to demonstrate the COG needs to be, but it's hermetically sealed. Okay, and there is no oxygen cannot be leaked. Okay, unless it goes through the hoses to the masks, delivered to the masks. Okay.
Yeah, now I got it.
Okay, thank you for the questions.
Okay, thank you.
So
Thank you all for the attention.
thank you for your presentation. It's very nice, very useful. We get a lot of information, for very interesting information. So I hope that for our students it will be useful.
Okay, and I'm like everyone else, like Rafaela and Clarissa said, we're always available, okay, to answer questions whenever afterwards or anything like that. Yeah.